Hello, I'd like to discuss a few things that I saw in the homework 4 and 5 and just give you a little advice how you can approach this problem so that you don't make the same mistakes on the test. Homework 4, I want to talk about specifically problem 1, 2, and 4. Although quite a few of you have made some mistakes in the problem 3, there's nothing new I can add to it. I discussed it in lectures in detail, so I would refer you to the lectures to look up for the method of solving this with both the dsolve command and both the Laplace transform. Alright, so problem 1 is talking about the function that is just a hat-like function like this. So it's or a tent-like function, but it is repeated many times. So this is the actual graph of the function. And when we take the Laplace transform of this function, now what we really need to do is to take the Laplace transform of a single period of the function. And I'm going to say that t belongs to the interval from 0 to 2a. And then multiplied by either the sum, so k goes from 0 to infinity, of e to the minus, the period is 2a s. Or if you want to do it, we can replace this with the term 1 over 1 minus e to the minus 2as. So either one is good for the Laplace transform, and many of you did find the correct Laplace transform of a single period of f, but many of you have forgotten to include the summation term. And the Laplace transform of f is therefore, if you use Mathematica, then Mathematica gives you 1 minus e to the minus as squared over s squared. But then you have to multiply by either this fraction, or I would prefer to multiply by the summation of e to the minus 2as. Correction, there's k inside. Alright, what kind of difference does this make? So I'm going to look at the inverse Laplace transform of the function 1 minus e to the minus as, space between a and s, squared divided by s squared. So let's look at the Laplace transform. That's the function. Let's plot the function. Since plot does not know what the value of a is, we're just going to say temporarily that a is going to be, well, let's just say 2. Well, that's just one period of this function. So what if I start to include the summation term? So we want summation of e to the minus 2a s k, where k goes, well, how many terms do you want to add? I suggest we add just 2 terms, just to see what kind of difference that will make. So I'm going to call this function Laplace transform of f, so LTF, this. And I'm going to plot LTF from 0 to 10. As you can see, I added a few more iterations of this function, but only 3 because I added the 0th iteration, 1 iteration, and 2 iterations. The more summation terms I include, the more iterations I will include in my function. So what happens when you forget to do exactly this? I mean, the summation, include the summation in the problem 4. So when you solve the problem 2, the Laplace transform of y will then become this Laplace transform of f. So let's just say that this is going to be Laplace transform of y. Not Laplace, inverse Laplace transform of y. And then the only thing that was added is the term s squared plus 9 in the denominator. So this is supposed to be the Laplace transform of y together with the summation term. If we forget to include the summation terms, you will get the output of the system as if there is only one period of action f applied to the differential equation. Compute that, and let's plot it. So again, I need to set a temporarily to be something. Let's make it 2, and we are doing the inverse Laplace transform of y, and let's plot it for a large interval of t values. Let's just say 0 to 100. This is what you can see. As you can see, right after 42, about 45 or something like that, the function stopped being what it is, and it's just because I only had this many f terms applied to it. If I increase the summation from say 10 to 30, then that will give me more periods of y correctly computed. So this was my comment for the homework 4, is that a lot of you have forgotten to add the summation term to your solution, and as a result you did not compute the correct solution y for the differential equation. Next thing I want to quickly mention is problem 1b for the homework 5. Many of you have gotten the system transfer function to be 1 over s plus 2 squared, which can be rewritten as 1 over s squared plus 4s plus 4. So you can see that the Laplace transform of y will be 1 over s squared plus 4s plus 4 times whatever the function I have on the right hand side. It's Laplace transform. Well, if I multiply by the denominator, then I get y of s times s squared plus 4s plus 4 should be equal to f of s. And then when I apply the inverse Laplace transform to this, I'll get that y of s times s squared turns into just y double prime of t, assuming that the initial conditions were 0. 4s times y has the inverse Laplace transform for y prime, and 4 times y of s, its inverse Laplace transform is 4y, and that's going to be f of t. This is what I was asking in problem 1b, just to reconstruct the equation that y is supposed to satisfy. And you can see that the coefficients for the equation and the coefficients for the denominator you have in your system transfer function are actually the same thing. And it's really not that hard to get the system transfer function from the equation or go back from the system transfer function to your equation. So I hope this clarifies some questions you might have about what went wrong in your homework submission, and I hope this will help you on the test. Thank you for listening, and good luck on the test.